Welcome to today's video. Today we are going to talk about one of the most important notions in mathematics, and at least in this semester, we're going to talk about vector spaces. Basic idea of vector spaces is to provide a framework that will help us formalize the notion of different structures of solution sets. We'll use this to formalize geometries. For example, we'll be able to describe what a point, a line, a plane, and so on is in dimensions 2, 3, and higher. We will be able to explicitly describe what we mean by the dimension of a space. And we'll be able to derive concise descriptions of a number of spaces that typically occur as solution spaces of systems of linear equations, but also in lots of other contexts. We'll start with the most prominent example, that is the space R to the n, and then we'll generalize the notation somewhat. We'll have a look at more examples for vector spaces in one of the next videos, and then we'll apply this theory to the system of linear equations that we've discussed already, so that we will be able to characterize the solution spaces of systems. So this introduces the chapter vector spaces. I've said the basic idea is to provide a general framework that will enable us to characterize solution sets of systems of linear equations and much more. And as I said, these vector spaces will appear in many different contexts in the first half of this lecture, in the linear algebra part, as well as in the analysis part. So that is a pretty abstract concept, and it is probably complicated to grasp at first. But there's always this nice example of R to the n. Most of the things that we will do actually live in some R to the n. So you can always fall back to that. Well, that's why first we'll have a closer look at the vector space R to the n. So we'll define what vectors in R to the n are and how we can operate with those. And this is basically just a formalization of the rules that you were applying anyway already. So don't worry about that too much. We'll start with a set R to the n. Just to remind you, what that actually means is R times R times R and so on, n times. So that is the set of n tuples with n elements, and each element is from the set of real numbers R. So that is the set of n tuples with elements in R. And more precisely, what we mean by that is R to the n. We usually write those n tuples in the form of a column. And that's just a convention. That's not fixed. You could also write them in the form of a row if you wanted to. But for us, if we talk about vectors in R to the n, we usually use column notation. So a vector in R to the n looks this. You have entries a1, a2, a3, and so on, up to an. And all of these entries are contained in the field of reals. So this is r to the n. We'll call the elements of r to the n, so these tuples, we'll call those vectors or points. And the entries in those vectors will be called coefficients, components, or elements. So let's first formalize that. Each element of r to the n is called a vector or point. AI is its ith coefficient, ith component, or ith element. So we'll use these interchangeably. Sometimes we want to emphasize the difference between a vector and just a number, a real number. And that is why sometimes we'll refer to a real number as a scalar in contrast to a vector. So to emphasize the difference, a real number is sometimes called a scalar. In contrast to a vector. Now, I've already said we will mostly be using column vectors, but for reasons that will become apparent later, it's sometimes useful to use row vectors as well. So we want to have a means of transforming column vectors into row vectors and vice versa, and that is why we define the notion of transposition. So for a vector, call that vector A. So usually we just denote vectors by small Latin letters, and the components then through indices like this. So we have a vector A that with elements A1 to AN in R to the N. We define its so-called transpose denoted by A, and then we have the superscript T for transposed by. Definition is simple. The transpose of a vector A, which is a column vector like this, A1 to AN. So that transposed is simply the row vector with the same entries. And of course, we can do the same for the row vectors. So if we take a row vector and transpose that, then the result is the column vector with the same entries. In particular, if we transpose twice, we're back to where we started. In particular, A transposed is A once again. Okay, I mentioned already, by convention, we usually use column vectors. And if we want to emphasize the difference between a column vector and a row vector, then we'll use just these names. We'll call them column vectors and row vectors. So by convention, a vector in R to the N will usually mean a column vector and its transpose is then a row vector. And finally, of course, we are able to do computations with these vectors, and that's probably the main part here. In particular, there's two operations that we use on these vectors. You already use intuitively. Just to make clear that this is actually a definition, we can add two vectors by simply adding their components. So, simpler part, we define a vector addition. We write this vector addition as plus with a circle around it, just for this definition here, to emphasize that this is actually not the usual addition of two real numbers, but the addition of two vectors. That might be something different, or it is something different, in fact. It's just very close, of course, because this vector addition is defined through the addition of real numbers. So it kind of inherits all of the nice properties of addition in the reals. So a vector addition plus is defined on R to the n through component-wise addition. So the precise definition is like this. If you have two vectors and you add them, so a1 to an and b1 to bn, then the sum of those is defined as the vector with components a1 plus b1 to an plus bn. And this addition here, that is the addition in the reals in R, whereas this here is the addition in R to the n. So that's why we use different signs here. We usually use the same signs, same operators later on. It's just that for this chapter, I'd like to emphasize that there is a difference. And this definition is more or less deliberate. So we could define the vector addition in different ways, as long as the addition is somehow meaningful, and we discuss what meaningful means in just a minute. Let me get to the other operation before we do that in more general framework. In addition to addition, we have one more operation, and that's multiplication. We cannot multiply vectors with each other. So for real numbers, what we can do is we can take two real numbers and multiply them, and the result is again a real number. That is not the case for vectors. There is no such operation on vectors. But there is a multiplication of a vector and a scalar, and that is called scalar multiplication. So what we also have is the so-called scalar multiplication of a scalar and a vector that produces a vector. Okay, so we have this multiplication. We'll denote it by a dot with a circle. And what this does is the inputs it accepts are a scalar, a real number, and a vector, an element in R to the n, and it produces an element in R to the n. See this as a function that takes these two inputs and then produces an output. And that multiplication is defined as lambda. So lambda is our scalar here. We usually use small Greek letters. Scalars if we want to emphasize the difference between scalars and vectors. So lambda times a1 to an. So this here is our scalar multiplication. And as I said, this lambda here, that's an element in R. And that is, again, defined component-wise. We just multiply each component with that same lambda. Right? And in here, what we have is the multiplication of two real numbers. So this is, again, multiplication in the reals. Okay, so basically that is what we need for a vector space. A vector space like R to the n is constituted by the set of vectors. And these two operations, and that is an addition for the vectors, produces another vector, and a scalar multiplication between a scalar, real number, a vector, and the result of that is again a vector. And just as a word of warning, please do not confuse scalar multiplication with the scalar product. Scalar product is something very different, and we'll introduce it in one of the later chapters. For now, we'll stick to scalar multiplication. So scalar multiplication takes a scalar, a vector, and produces a vector. The scalar product takes two vectors and produces a real number, a scalar. Well, as I said, we'll talk about that later on. For now, it's just scalar multiplication. Now, what this R to the n is, it's kind of a prototype for a more general concept, and that is a vector space. So I already said what we need is a meaningful addition and a meaningful scalar multiplication for those objects, and it doesn't really matter what those objects are. In this case, it's n tuples. Will be in most cases that we deal with, but there are also more exotic vector spaces. For example, we could talk about spaces of functions, we could talk about spaces of polynomials, and we'll see some more examples later on. So let's define the general concept of a vector space based on those observations. And in that definition, we'll discuss what a meaningful addition and scalar multiplication actually have to do. Okay, so this is the next definition. That's going to be a long one. That is the definition of a vector space. Now, a vector space, or sometimes it's also called a linear space, is a set V together with two operations. And these operations are the vector addition and the scalar multiplication. How those are defined, of course, depends on what the elements of that set V are. We just need to make sure that the addition is meaningful, meaning it's similar to the addition that we're used to, so that we can apply the rules for addition that we're used to. And what exactly that means, make that a little more detailed now. So we want a vector addition. Again, we'll denote that by a plus with a circle around it for now. That addition takes two vectors, so an element from V and another element from V, and it produces a vector, an element from V. And we want that this addition has the following properties. So the first property, we require the existence of a so-called neutral element. That is an element that, if added to an arbitrary vector, does not change that vector. There is a so-called neutral element of addition. We refer to that as n for now. That's an element in the vector space. And that is characterized by the property n plus a is a for each vector a. Now, let's try to apply this to the vector space R to the n. What is the neutral element in R to the n? Well, of course, that is a vector that has zeros in every component. Right? So the neutral element in n is the all zeros vector, that here. That is called the zero vector. Adding this to any other vector will not change the vector. That's the neutral element. Second, we'd like to be able to reverse an addition. So if we add a vector to some other vector, then we'd like to be able to get back to the original vector by adding something else. And this something else is called the inverse element. So what we need to do is, what we need to make sure is, for each vector A in V, there is a so-called inverse element. Denoted by, usually we denote this by minus A in the context of addition. Such that, what does it do, this inverse element? Well, if we take A and then add the inverse element of A, then the result is the neutral element. So adding A and its inverse does nothing. Of course, in R to the n, that's again easy. The inverse element of a vector a1 to an is simply the vector minus a1 to minus an. Because if you add these two, then the result of this addition is obviously the all zeros vector, and we established that this was the neutral element already. Okay, so these are the two important elements that have to exist so that we can do meaningful computations. Two more things we'd like to require is two laws, and we want this operation to be associative, and we also want it to be commutative. Define what that means in detail. So this is third point on our list. The operation plus needs to be associative, meaning for arbitrary vectors A, B, C in V, we have, well, if we add A and B and C, then of course we can do this with a different order. So it's not really clear what A plus B plus C means. It could either mean we first add A and B, and then we add C to the result. Or it could mean we first add B and C, and then we add A to the result. And what associativity says is this doesn't make a difference, right? So the order in which we carry out this operation in a longer chain is irrelevant. That's the associative law. And of course, this law holds in the real numbers. So for computation in the reals, this is associative, and that carries over to r to the n, simply because we define the addition as a component-wise addition of real numbers. And finally, we also want the operation to be commutative. Operation plus is commutative. And what that means is for two vectors a, b in V, we have a plus b equal to b plus a. So it doesn't matter which of the operands is on the left and which is on the right. And again, this is of course true for addition in real numbers, and that property carries over to r to the n due to our component-wise definition. So these four properties characterize a meaningful addition. That's an addition that we can work with basically in the same way as with the addition in the real numbers that we used to. And then we need the scalar multiplication. That's the second major point on the list. We want this second operation. That is a scalar multiplication. We'll denote this by a dot with a circle. That scalar multiplication takes a real number and a vector and produces a vector as an output. And it needs to have the following properties. And again, we want that to be a meaningful multiplication in a way. Actually, that's not as strict as with the addition because we do not multiply two elements of the same set. So that's a little more loose. But again, what we want is the existence of a scalar neutral element. So an element such that multiplying a vector by that element does not change the vector. So there exists a scalar neutral element. This element is usually denoted by 1, called the 1 element. Such that 1 scalar 1 multiplied with any vector doesn't change that vector. That's true for all a in the set V. And of course, in r to the n, that scalar neutral element is just the real number 1. And that is, of course, where the notation comes from, right? But again, for more abstract vector spaces, that might be different. We also want this operation to be associative. So the operation is once again associative. Meaning, if we take the scalar and then multiply that with a scalar multiplied with a vector like this, that is the same thing as first multiplying the two scalars and then multiplying the result with a vector. And notice that here we have a scalar multiplication, whereas here we have a multiplication in the reals. So this is a little strange in that it actually changes the operations. And that, of course, has to hold for all lambda mu in the reals and all a in V, as usual. And this is, of course, true in the real numbers, again, because the scalar multiplication is just defined component-wise. So again, this boils down to actually being the multiplication of real numbers. And the last point on this long list, getting there finally. Now that combines those two operations in a way. We want those to be combinable in the same way that real addition and real multiplication are combinable. And that means we want distributive law to hold. And in this case, more precisely, we'll have to formulate two distributive laws. Hold for the combination of this vector addition and the scalar multiplication. And those distributive laws are the following. The first is for the addition of two scalars and then the multiplication of the result with a vector. And distributive law, basically that means we can expand that by applying the scalar multiplication for each of those scalars to A first and then adding the result. So what we can do is first multiplying A with lambda, then multiplying A with mu gives us two vectors, and then adding the resulting vector. So that is the same for all lambda mu in R and all vectors A in V. And finally, the last distributive law. This is in contrast for the addition of two vectors. So if we multiply the sum of two vectors with a scalar like this, then that is the same as multiplying each of the vectors with that scalar first, and then summing up the resulting vectors. And again, that needs to be true for all lambda in R and all AB in our vector space. And again, this holds for the reals, for the R to the n, precisely because this holds for the real numbers and our definitions are all component one. And finally, last sentence of that definition, the elements of a vector space are called vectors. So if anyone ever asks you what a vector is, then the one correct answer would be an element of a vector space. Please don't say something like a point or an arrow or something like that. To round this off, let's list a couple of conventions to make our lives a little easier, because this notation, as you have already noted, probably this is a little awkward. So we try to make things easier by adopting a number of conventions. First one, we usually just write plus and a dot. So we omit the circle, and we also omit the dot when the meaning is clear from the context. If the meaning is clear from the context, we usually write plus and dot in place of plus with a circle and dot with a circle. Also, the dot may be omitted, as you used to from real numbers. So lambda times mu, we could just write that as lambda mu. Furthermore, we'll adopt the convention that the dot operation, the scalar multiplication, binds stronger. Yeah, so we don't need that many brackets. So we adopt the convention that the scalar multiplication binds stronger than the vector addition. And what I mean by that is an expression like lambda dot a plus b means, more precisely, lambda dot a first, because the dot binds stronger, and then sum the result with b. Same as with the real numbers. Yeah, again, you're used to that. You will have noticed that we did not consider commutativity for the scalar multiplication, and that's because it doesn't make sense, really, because the arguments are of a different class. We have a scalar and we have a vector, so interchanging those doesn't really make sense. Still, it's sometimes convenient to just adopt that same notation. So the order of those two won't matter. We always mean the same thing. And that's, again, a convention that we'll adopt. So we write a times lambda instead of the correct way, lambda times a. But we mean the same thing. So we just use whatever is more convenient in the given context. Two more. I already said the neutral element of vector addition has a special name. It's called the zero vector. Neutral element of vector addition is called zero vector and is denoted by either just 0 or, if you want to stress that it's actually a vector, we sometimes use 0 with an additional line like this. So that's the all zeros vector, or the neutral element in the more general setting. And finally, one notation that is specific to R to the n will define a set of special vectors, the so-called unit vectors in R to the n. We will use ui for ith unit vector, or often ei, that comes from the German notation Einheitsvektor, to denote the ith so-called unit vector. And what I mean by the unit vector is, well, EI is the vector that has zeros everywhere with one exception, and that exception is there's a 1 at position I. So this here is the ith element. And the length of that unit vector, of course, depends on which space we're talking about that adapts, right? So for example, in R2, we have the unit vectors E1, 1, 0, and E2, 0, 1. In R3, the notation is the same. We again have E1, but the vector looks different because it, of course, needs 3 coordinates now, right? So E1 is this, E2 is this, and E3, there's also an E3 now, looks like this. Of course, for R4, R5, and so on, this list extends. So this concludes our introduction to vector spaces. That has been a long video and a pretty abstract one. We'll have a look at some examples in one of the next videos, and then we try to apply this new knowledge, this new framework to the question of characterizing solution spaces. I'll see you then.